Vector integrals in the physics vectors package. That package now includes an updated int, lowercase I, and an int with an uppercase I, is a pair of commands, and the update implements a collection of vector integrals. Now, what are vector integrals? And how did they relate to the existing integrals available through calculus, basic calculus, and in the student packages, VectorCalculus and MultivariateCalculus? Well, in this webinar, we're going to take a look at what these commands do and want to relate their functionalities to the existing functionalities in Maple and show how the existing syntax-free tools in the context panel and task templates apply. Most of the exposition is by example, so there are 8 new vector integrals. So there are at least 8 examples, and in fact there are 10 examples, and each illustrates a concept showing the full array of Maple tools, the old ones and the new ones. Now, as this webinar was being put together, there were updates to the physics package taking place, and so it is advisable to be sure that the correct version of physics updates is installed, and I'm going to show how that's done momentarily. To determine the state of the physics updates, execute this command. It'll tell you the version number. If you want the latest version, you could execute this command. I've used version 1308, dated from August 26th. Now, the help page that you access by typing the question or executing this command, physics : vectors : int. That help page will contain these 3 categories of integrals. These are called path integrals, surface integrals, volume integrals. 3, 3, and 2. That's 8. And this is what it looks like when you look on the help page, and this is what we want to explain. Well, when I began this project of looking at what these new vector integrals were, I had in my head things that I had already used in the past. What are those things that I was saying? What compares to what? Okay, so I wanted to find out, how does one integrate a scalar with respect to arc length? This is the typical path integral of a scalar. Tangential component of a vector field. Now, this is work or circulation if the path is closed. F dot n ds, that's the normal component along a curve. That's flux through a plane curve. Scalar d sigma on a surface, so this is a surface integral of a scalar. This is flux through a surface, F dot n, normal component of F, integrated on a surface, and a volume integral. So these are the 6 things that are in my head saying, this is what I know. How does this new int command in vector, in physics vectors, how does those 8 integrals, or how those 8 integrals reproduce these quantities? Let's explore the first category of these new vector integrals, line integrals. What are the basic types of line integrals? Remember, there were 3 listed on the help page, but here I have 4 listed. This one is not on the help page. F is a scalar. this is a vector, and it results in a vector of line integrals. And I've never seen that before. This means the norm of this vector, so it's implemented with the word norm, and that's the one that gives you FDS. This is what you even see in elementary calculus as a line integral with respect to arc length. Vector dot vector. Well, that turns out to give you the tangential component of f along the curve, so this is work with circulation. This I understand, this I've seen. F cross dr, vector cross dr. So you have this vector, assuming it's components of FGH or FGH, cross. What would be a representation of dr? Well, here's one representation, Cartesian coordinates. Take the cross product, you will get a vector with these integrals. Now, if you look down here at the third component, let's assume that h is 0, so you have a plane. That means this will be 0 because h is 0. Z will equal 0. You're in, z dot will be 0 because you're in a constant plane z. Z dot would be 0. H would be 0. So these two integrals would not be there. And this is the flux integral, f dy minus g dx. This is the flux integral for a plane curve. It's the normal component. So these are the normal components integrated along the projection of a space curve onto a coordinate plane. That's the only sense I can make out of this. Now we're going to do some examples, and there are some commonalities in these examples. So this is the initialization. Typical, restart, bring in physics vectors, special notation in the physics vectors package. If I want to get into student vector calculus, I'll alias the long name to VC, multivariate calculus, MC, and if I'm in vector calculus, I want vectors to show up as column vectors, not as sums across basis vectors. In the physics package, you represent vectors this way. You use I, J, and K. They special notation, unit vectors. This is a scalar. This is the comparable vector field in vector calculus, YZ, XZ, XY. And these are two position vectors in the physics package, again represented as a sum across these basis vectors. There is a new command that goes along with these vector integrals, and that is this command parameterized curve. This is the way curves are parametrized in this package. So let's just take a look at a couple of examples. Here's a plane curve, y equals x squared, but z equals 0. The parameterization is x of t equals t, y of t equals t, t squared, and z of t equals 0. T is the parameter. You could output this as a vector, and you would get ti, that's the I component, t squared j, that's the j component. Clearly the z component is 0. If you give it a vector, x, x squared, I, and j, it will come back as x of t is t, y of t is t squared, z of t is equal to 0. Give it a circle, x squared plus y squared equals a squared, it automatically switches to polar coordinates. Ask for the output as a vector, and it switches to polar coordinates in vector form. Ask for the basis in cylindrical coordinates, and that circle will come back in cylindrical coordinates. decide that you want the parameter to be something other than t. I took the Greek letter for t. And now you see that x is the square root. It's plus or minus the square root here. Okay? So whereas when you let the command pick the parameter t, it recognizes the circle. Here, it does not recognize the circle because you've given it a different parameter name. Here is rho. Now, rho has a special meaning in the vector in the physics package. It's the radius, so it implies a coordinate system. And here you have the curve parametrized by these equations. Rho is a, phi is t. There is this line option, P1 to P2. You get the parametrization, and if you look carefully, it's the equivalent of P1 plus t times P2 minus P1. So t goes from 0 to 1. If you switch the direction, P2 to P1, then it's P2 plus t times P1 minus P2, and that will be different. But it will still go from 0 to 1. Now I said, what happens if you give it an ellipse? Okay, it's not recognized as an ellipse, nothing special, and it's solved for x. So the parameter is y. Well, let's see what happens if you give it a plane. In fact, this is two planes, and they're intersecting. So there's your line. The parameter is t. Give it a sphere intersected by a plane. That's a circle in space. Well, look over here. The parameter is y, and x and z are solved for. So these are some of the issues that you would have to contend with if you parameterize a curve using this parameterized curve. Let's do some examples. We've got 4. Here's the first one. A pair of integrals, f ds along the curve, but the curve is a straight line from P1 to P2. And this is f, this scalar, dr, that's that vector thing. Here's my scalar. So let's see what these two integrals are. I'll call the first one a and the second one b. Let's look at the solution to the first integral. This is a trick that you'll see in the help page for these vector integrals. Int equals int applied to. So what happens is with the uppercase I, you get the unevaluated integral. Lowercase, you get the evaluation of the integral. This is f ds. This is the basic calculus line integral of a scalar along a curve. It's implemented by the use of the actual word norm of dr, and that underscore tells the package that this is a vector. And that's equal to P1 to P2. So this range tells the command which way you're integrating along that line. And the line is given by this keyword, path equals line, P1 to P2. And here you can see the unevaluated integral, P1 to P2. The dr has these norm bars around it. So here you say norm, and here you see norm bars. This is the value of that integral because you got this scalar xyz. Now I've written down all four possibilities of P1, P2, and the line P1, P2. Switch P2 to P1 here, but leave the line intact. Leave the switch here, P2 to P1, but switch on the line P2 to P1, and P1 to P2, and switch here, P2 to P1. What will the sign of the answer turn out to be? Okay, so if I write P1 to P2 here, P1 to P2 here, and I put inert in the command, then this left-hand side is the same as this left-hand side, and it also includes the word inert. But on the right-hand side, you see the unevaluated integral itself. So here's the integrand. This is your ds on that line. That the arc length is square root of 86, and you're integrating 0 to 1. So whatever this turns out to be, I guess it's this negative number. If you make a switch in P2, P1 here, the endpoints are flipped. So you would change the sign of this answer because you have flipped the endpoints, because you've gone in the opposite direction. Now, if you change the description of the line and go in the opposite direction, then you're going 0 to 1, but you pick up a minus sign. So you change the sign of this because you are integrating in the opposite direction. Apparently, the description of the line here is not as essential as the order of the endpoints here. And if you say P1, P2, so you're going from 1 to 2, and you describe the line otherwise, P2 to P1, you get two minus signs. You're going to flip this, that's a minus sign, and you picked up a minus sign here, so you're going to get this answer. So the direction that you use in the description of the line won't change the value of the integral. It's the direction that you established by stating here what is the initial point and what is the final point. We can verify this result by using the pathInt command in the VectorCalculus. Scalars don't carry a coordinate system, so you have to name variables x, y, z. But a line is recognized as an object, and you give the line beginning point, end point as vectors, and you notice you get this minus 13 over 6 square root of 86. If you reverse the two endpoints, you get the same number. So internally, the parameterization is being taken appropriately. We can have a verification from first principles using the multivariate calculus package. There is a line command. You give it 2 points, P1, P2, as lists. Wrapped it with get representation, and the return of the form of the line can be controlled. I choose parametric. This parametric form is comparable to what the parameterized curve command produced. So the parameter goes from 0 to 1. You evaluate the scalar using these equations, and you get the integrand that you see up here, same integrand. Then you got to compute ds. Okay, so you differentiate this with respect to t. You get a -6, you square it, you get a 36. Here you get a 5, you square it, you get a 25. And here you get a -5, you square it, you get a 25. It's 86, root 86. You put that here. Do the integral 0 to 1, and you get the same number that we got here. We can also do a syntax-free verification using the context panel. So if you have the Student Vector Calculus package installed, the context panel raised on the scalar XYZ will contain the option Student Vector Calculus, Line Integral, 3D. If you pick that, you get this dialog that comes up. And you can see that the command that's underlying this recognizes either a line segment or even a polygonal line, which the int command in physics vectors does not. It recognizes a circle or the general curve, which you give parametrically in a vector form. Okay, so this is just a line segment, P1 to P2. Down here you have the choice of returning the value or just getting the integral. You pick integral, this is the integral you get, and we know that what the value of this is going to be. So for the second integral here, 1b, the variable of integration is this vector dr. So again, int, there's your scalar. The dr as a vector is indicated by r with the underscore, which is in the package, has special meaning. P1 to P2, that's the direction along this line segment. Use path equals. You get P1 to P2, scalar, and dr as a vector, tells you the path. And the answer is a vector. It's a vector of integrals. We can verify this result. Let's go to the VectorCalculus package. In either of the VectorCalculus packages, the int command maps automatically onto vectors. So here we have the int command in VectorCalculus. Here is the scalar evaluated along the line. We did that earlier. This is the integration vector dr, right? Minus 6, 5, minus 5. And integrating 0 to 1, we get this vector of integrals in the coefficients match, which you see here from the physics vector command. And if you want to look at it as an integral vector of integrals, here is a vector, and I put 3 integrals. Here is the scalar. This is dx, this is dy, and this is dt, and it comes out to be the same vector as we had here. In a second example, we're going to look at line integrals along the straight line from P1 to P2 of these two vectors dotted and these two vectors crossed. I've defined that vector here earlier in the initializations. A solution of the first problem. You can see here int. This is the vector, right? This is the notation we use to name that vector in the physics package. This is the dr as a vector, P1 to P2, so there's how you establish the directionality along the line, which you describe by saying path equals line. Here is the unevaluated integral. Its value is 32. To verify this, we could use the lineInt command in the Student Vector Calculus package. lineInt applies to vector fields. G is the vector field equivalent of this vector. Along the line, that's all you have to say is line. You give the start and end points. You get 32. And this can be done syntax free. If you have the Student Vector Calculus package installed, not just reference, installed, and you type the name G and it echoes back and you have the vector field G, you'll find in the context panel for G, Student Vector Calculus, the option line integral. You can thereby open the line integral domain dialog, which is this dialog here. Since we are doing a line segment, we simply give the endpoints here. We could integrate over a circle or over a general curve, which would be given as a parametric form in a vector representation here. The integrand, integral from 0 to 1, it's what you get when you say integral. If you say value, you will get the value, and it will turn out to be 32. The solution to part 2, where you have the integral of this cross product. So let's set that up. Int, there's the vector. There is the vector form of the integration variable, P1 to P2, because you're along a line, and you have to say here, kind equals cross product. And so on the left, you get this representation. There's the vector field, cross dr. It turns out to be this vector. By way of verification, we use the VectorCalculus package. We need the cross product of G with dr. Now, dr is this vector, but it has to be represented as a vector field. Okay, so all of this represents dr as a vector field. And we take the cross product of the vector field G, evaluated along the line, but we've gotten that earlier, call it L, so this is a substitution here. Cross product is taken, integral is mapped onto the components of this cross product vector, and we're integrating 0 to 1, and you get these numbers 5, which is this 5 here, minus 13.6, that's the J component here, minus 49 over 6 is the K component. In the third example, we go back to the same two integrals that we did in the first example, but only we changed the curve. Instead of being a line, we make it a space curve. The solution for part A is here. Int, norm dr, that gets you ds. These are the initial and final points along that path. Now the path is y equals x squared, z equals 2x. If you think of x as the parameter, it's going to be 0 to 1, so it's going to be 0, 0, 0. And at 1, you're going to get 1, 1, 1. 1, 1, 2 rather. 1, 1, 2. Okay? Along the path described by these two equations, path, put inert here, I see the representation unique to this physics vectors package, and this is the integral you're going to evaluate, 0 to 1, this integral. If you remove the inert option, then on the right-hand side with little I, you get the value of the integral. We can verify this with the path_int command in the student vector calculus package. Path_int, there's your scalar, xyz. Scalars don't carry coordinate systems, so you have to give the variables xyz. Path is the general curve given as a vector, x, x squared, 2x, and x goes from 0 to 1. Return is the same number that we see here. There's a syntax-free access to this verification. In Student Vector Calculus, if it's installed, the context panel on the scalar xyz will open to this option, line integral 3D. You get the path integral dialog opening, path integral domain dialog. We are doing a general curve. The integration variables are x, y, z, and you see here you give it as a vector t squared 2t. Parameter t goes from 0 to 1. If you return the integral, you get this integral, which matches this integral here. For the solution of the second integral, the evaluation of the second integral in the vector physics vector package, int here, scalar, the vector r, that's representing dr, initial and terminal points, and the path of integration is given by these two equations. Without any other options, you get the value of that integral, and it is a vector as a result. We can verify this result by using the int command in student vector calculus. It maps automatically onto vectors. So what vector does it have to map onto? Well, first of all, this is a scalar. We have to make the substitutions. X is x, y is x squared, z is 2x. So that's what equate sets up. X equals, y equals, z equals. And then the eval command makes that substitution into f. So all of this is the integrand for each of the integrals against dx, dy, dz. Remember, x is x, so you get 1. Y is x squared, so you get 2x. Z is 2x, so it's 2. You get this vector of integrals from 0 to 1. And the numbers here, 2/5, that's I. 2/3, that's j. And 4/5 is k. The fourth and final example of these line integrals, we have vector, vector, vector cross vector, vector dot vector, vector cross vector along the space curve. Instead of earlier we did it on the line, now we're doing it on the space curve. The evaluation of the first integral, int, this is the vector, this is the vector dr vector, right? Maple looks at these two and says, okay, it has to be a dot product. Initial point, terminal point, along this path. If you put inert, you actually get to see the integral you're going to evaluate. If you take away the inert, the integral is evaluated, and it's 2, and you can see that it's going to be 2 t cubed over 3. You get a 1/4, 8 over 4, 2. There you go. We can obtain that integrand stepwise. If you apply the Parameterized Curve command, you'll see that this pair of equations comes out t squared 2t, parameter is t. That means the vector r underscore is t squared t with ijk, and so dr is going to be 1, 2, t2 with ijk. The function f evaluated on x equals t, y equals t squared, z equals 2t. This becomes the vector form evaluated on the curve, 2t cubed. That's I. J is over here, 2t squared and t cubed. If you dot f with dr, this is f, this is the dr, you get 8t cubed, which is what you have here. Additional verification can be obtained through the student vector calculus package. Use the line int command. This is the vector form in the vector calculus package, vector field. Path is the generic curve. X squared 2x, x equals 0 to 1. You can get this command to display the integral. Here I've just gotten the answer 2. Syntax free. You install the student vector calculus package in the vector field G. Right click on or bring up the context panel on the vector field. You see the option line integral. You get the line integral domain dialog, which is here. General curve. You give the path as this vector. It's really a parametric form, but 3 components are put into a vector. 0 to 1 is the domain. You choose integral rather than value, and you see you have this integral at cubed, which matches the at cubed you see here. The solution of the second part, vector cross vector. So int, this is the vector, this is a vector, beginning point, end point along this path, and you include kind equals cross product, so you get the cross product of these 2 vectors. Inert means you'll see the integral, and if you remove the inert, you'll see the value of this vector integral. The integrand can be obtained stepwise. This is the cross product. ijk, this is a determinant. This is the vector f evaluated on the curve. And this is dr, 1, 2, t2. That equals this vector. And if you clean it up a bit, you can pull out a minus 2t squared from each component, and you get minus 2t squared times this vector. Now, go back up in here. I just grabbed this piece right here. I left the minus 2t squared out. I grabbed this piece. I brought it down here, and I applied the collect command with respect to the component I, the variable I, and you get this vector, t squared minus 2, which is that, 3/2 t, which is this, and 1 minus 2t squared, which is this. So just doing this cross product by brute force, you see that this is the integrand. We can verify using the vector calculus package. First of all, we need to evaluate G, the vector field, on the curve. Then we need to form dr as a vector field, and that's 1, 2, t2. That's this chunk. And then int automatically maps onto that resulting vector of that's produced when you put cross product of those 2 vectors. Integrate from 0 to 1, and you get 14 over 15, that's this component, minus 3/4, that's the j component, and 2/15, that's the k component.